A very good afternoon to one and all who are gathered here. I have the pleasure of introducing to you our honorable resource person of this session, Dr.M. Muthukannan sir, Professor and Head of the Department of Civil Engineering, Kalasalingam University, Srivilliputtur, a renowned researcher and teacher. He is having more than 20 years of experience in teaching and research. He has acquired a UG degree from Madurai Kamaraj University, PG degree from College of Engineering Guindy, and PhD from College of Engineering Guindy, Anna University by the year of 2010. And he is specialized in transportation engineering and concrete technology. Dr. M. Muthukannan sir is not only a talented teacher, he is an active researcher. So far, he has published 24 international journals and 10 national journals and 35 international conference papers. He published a number of patents and books. Recently, he received the project from DST and TNSEST at worth 2.38 crores. He is a life member of various societies like Institution of Engineers, ISTE, ASCE, Institute for Transport Management, Indian Institute of Urban Transport, life member for Society for Advanced Management Studies, and he is a member of doctoral committee for 3 students in Anna University. Our resource person has actually participated as academic council member, BOS member to various autonomous engineering institutions and has given more than 35 guest lecturers to various engineering college students and faculty members. I hope today's session will be enlightened with some knowledge of our resource person, Dr. M. Muthukannan sir. Sir.
Thank you for your wonderful introduction.
Thank you, sir.
I thank the Almighty and the management of FX, and especially Dr. Kannan for giving me this opportunity to present before this August gathering. And I have troubled Dr. Kannan a lot because my session was in the morning and I asked him to reschedule in the afternoon. Patiently, he revised the schedule and he accommodated me. And a special thanks to Mr. Karpasamy sir, Dr. Karpasamy from SRM University, and he is my friend, and he readily accepted my request, and he changed the schedule. And I request my apologies to the participant also, because to kindly bear with me because of the scuffle in the schedule. So today, the introduction part, they have given a lot about me, so I know no need to tell about me. And just I want to make a small correction that I am not the head of the department. I was a former head of the department, and the number of research paper when I submitted this introductory resume to Dr. Kannan, it was 26. Now it is 30. So this is the thing. Then another some DST, the TNSEST fund also been received. So this is the update for the last 1 month or 2 weeks. Okay. So with this, I will start my seminar. So the data input, data output, the spatial data analysis, integrated analysis, spatial and the data the attribute data. So this is the topic given to me. So all the things that comes together called as a data. So for example, if you want to do analysis, the first thing is that you need some data. If you without having any data, you cannot do any analysis. For example, if you want to find the number of students who are there inside the classroom, who are that is a good, bad or poor based on the academic performance or based on the physical performance or any performance. So you should have a complete set of data, who you are going to assess, whom you are going to assess, what you are going to assess, and when you are going to assess. So without knowing anything, that you cannot do any analysis. So the fulcrum of this today's seminar is how to handle the data of different types. That is the outcome of today's seminar will be there, where we are going to learn about what are the data input and what are the data output. What is the input if you give? What will be the data output will be there, and in middle, what are the spatial data analysis you are going to do, and how we are going to do that integrated analysis, and you are going to acquire the attributed data. This is the total outcome of the seminar for today. So we will be going with this here in the alignment with the data input and the data again and again. We will be speaking about the data. Kindly bear with me, because without data you cannot do anything. So because that is a remote sensing is a technique where the remote sensing and GIS is a technique. Earlier, if you want to survey that is a survey area, you need to take a theodolite, you need to take a that is a crash staff, you need to take a chain, and you have to involve in many persons, and you have to measure that area left and right and to the top and bottom. It will take them some years and even months and years to procure the data. So, but the data is a precise data, but no doubt. But the problem is the time. Now, if you want to if you want to take a data, now what you're going to do, you are going to just go to the Google and you can take the data. Now the Google map is available. Earlier, if you want to go to some place, you need to you need to know the language. You need to know the road map, etc. So all the things put together, then there will be a lot of confusion. Now it is not like that. You have a data in your hand as a Google map. Just you are going to press it. Yes, this is my origin and this is my destination, and it gives what is the average time, what is the maximum speed, minimum speed, and it gives what is the estimated time of arrival. Everything it is given in the single platform. So this we call as a data. How it has been arrived. It has been arrived based on the collection of data, so that it gives the shortest route, which is the longest route, avoiding toll gate, everything. It does the analysis and giving in the presentation form to you. So the data it is in that is a worthy one where you are going to do the different type of analysis. With that analysis, you are going to give the presentation. Google is doing a lot of analysis, so it gives procure the data from the from the people, and it does the analysis and it give it. Now you can see that, for example, the Google or Yahoo or Amazon, they give the service at the free of cost. They are not giving any service at the free of cost. They are procuring the data. They are procuring the data of Dr. Muthukannan, where he is going, where he is sitting, well, Monday where he went, Tuesday where he went. All the data have been collected, and the data has been sold to some person who is interested in Muthukannan. So what he does is he do some analysis. For example, the importance of data I am saying. Just there's a few months back, where I visited a store in Dindigal. And I was checking for clothing apparel, and I was making a debate with them, and I could not procure that because due to some technical problem, and I don't like that color and other thing. But that is while entering into that showroom, I was being monitored. While I was away from that's a showroom, what happened was that again I've been monitored whether I have paid by using my cell phone or the data card, because all the data are integrated, because my credit card and debit card is integrated with my cell phone. My cell phone is integrated with the Google map. Google is taking all my data. That's all. So I have not paid anything that has been arrived, because even if you are paying with a cardless or cash, they are asking the phone number. When you give a phone number, this phone number has been integrated with the Google. So what happened is I didn't purchase anything, but I was traveling towards Bangalore. But unfortunately, while I am entering near Salem, I received a message from the Google that nearest that's a clothing apparel is in the nearest proximity. You can again try it, and it gives the list of that stores which is available. So they are doing that. They are tempting. And they are saying that what are the materials I have seen. So they are giving that's a choices such a way that they make me to process the particular item and make me to purchase it. So this is the data analysis. So they do lot of data analysis and they want to sell a product. So like that, like our civil engineers, what we are going to GIS or remote sensing engineers, what we are doing, we do lot of data analysis and we process the data and we are going to give it. But in doing the data analysis, what are the problems you are going to face? That we are going to discuss. That's all. Do you understand? So only the people are seeing the output. Now we are there as a technical person, where we are going to say what are the things which we are going to do it. In that, what are the problems which we are going to face and how to overcome that problem. For example, that I'm making a map. In the that's a map. I have taken a digital map, and the digital map it is a complete data set of data. But I have taken that is a photograph during in the month of April and May, and that is the same that's a latitude. I am taking a photograph during the month of November. So both the photograph, it is having some 100% difference. Why? Because that is for example, if there is a water source, the water source will be during the April and May, it will have only the dry nature. There will not be any water. There will be no source of. It will be looking like a plain land. That's all. But when I take a photograph during the November, what will happen is that is all the water bodies will be filled with that's a water. Now it will have a different that's a nature. Now a person who is having the same photograph of a different period will be getting confused. So now what you're going to do, you have an interpretation of result. So this is the water body. So you are going to make an overlap and you're going to do it. And some points may be missing. Some due to the scatter of that scatter. I think that you in the previous sessions they have covered about the scattering. So the scattering it is very because of the scattering that there may be some data missing. So how we are going to assess the data and reclaim the data. So this is that is a work that we are going to see it in this that is a lecture. That is a data, how the data input and what is the data output, and in between that, what are the spatial data analysis, integrated analysis, and the data attribute data, spatial attribute data that you are going to do it. So that is the introduction. That is the putting data into a computer called as a data coding. That is the coming directly to the GIS part. That is putting a data into a computer called as that's a data coding, where the fundamental process for virtually all projects we need some data coding. We need some data. So how the computer works, zeros and one. Like that, our concept is also like whether it is shaded or not shaded. That's all. It is available or not available. That's all. Do you understand? This is the thing that we are going to make it. So the recall the spatial data, it is acquired from the various sources and it has the different formats and it can be captured at the inputted at the several methods. Once the data is contained with the GIS, nearly all data must be corrected, manipulated, and fit to the model and chosen for the data access. So this is the important thing. When you are going to get all the data, you can do a lot of wonders. If you are not having the sufficient data, you cannot do any analysis. The analysis may be wrong. You may that is come to a conclusion that this may be a valley, there may be a hill, there may be that's a water body, there may be actually there may be it may be a desert. So these are the things that you need to understand before the data analysis, where we are giving that's the analog versus digital data. First, sir, you can ask me what is the requirements, sir? Why you want to go for GIS? The analog data is a non-electronic data, must be converted digitally prior to using the GIS. The analog data is the normal map. With the map, there are a lot of disadvantages. What are the disadvantages? For every time you need to correct it, you have to redraw the map again. Again and again, you have to draw it. But now it is not required. Just by clicking one, that is a in the left click or right click, it is very easy that you can erase it. So erase the complete that is a polygon or line or anything very easily. So this is the thing. But first, the analog data, the paper should be converted into digital form. So how to digitize it. So the digitization is a technique where you are going to scan it and you are going to make a layer. And after in the layer, you are going to mark all the components, and you are going to get the result data. In childhood, you might have done with the tracing paper. You might have taken the tracing paper, and you have kept over any diagram, and you might have drawn that. This we call as a digitization. If you are doing in the tracing paper again, you call it as analog. If you say doing same thing, scanned, and if the one layer is inserted as a CAD layer, and over that you are going to give another one layer, and you are going to draw it, that you call as a digital form of a particular data. Do you understand? So now the analog or that's a non-electronic data must be converted digitally prior to the using into the GIS. Where that is an example. For example, the printed aerial maps, photographs, paper maps, etc. This is called as a analog data, where it need to be converted to a digital data format from the computer. For example, satellite images or GPS data, etc. These are the data you should call as a digital data. So the data input method, how to give that's a data input by means of a keyboard entry. You can convert in the file by the way of computer terminal. By example, entering the names of for the different that is a signs in that street. And that's next is manual digitization. Request the digitization table and connected to a computer station, and you are going to digitize it. So digitization table, you might have seen that it is in the scanner, or it can be a that is a pen, or it can be a rolling scanner. Anything it may be in the form that it need to be converted into a digital form. Do you understand? So next is the automatic digitizing. The scanning is the most common one. Example, the scanning of an old map or a photo in a digital format that you call as automatic digitizing. You send the photograph inside, it will convert this that is a analog data into a digital data, and it will give a clear picture. That is a scanning. Our photocopying that is a the notebook or any table. That is also called as a that's a automatic digitization, where it is digitized and it has scanned and it has given. Now you are going to take that as one layer, and you are going to put another one layer over it, and by using the AutoCAD you are going to draw it. This is called as a automatic digitization, where for the equipment which is required, that is called as scanning. When scanning the analog data, the several problems can occur. So normal problem is that is an optical distortion, because there may be change in the optical distortion. Unwanted data like the coffee stain and handwritten annotation, anything that it can be seen. For example, I'm going to scan this page. So now what I'm going to do? So unknowingly I have drawn a small line here. Unknowingly I have drawn a small line. The computer, what it will do is it will take this line as a one data. This line as a one data here. It will take this line as one data, where this line as a one data it will take, and it will have some other meaning. Do you understand? So the unwanted data or the coffee stain, anything, it will also be affected. Even a small dot like this, you have very small dot like this will also be accounted in a decision form, which you may neglect it. That you may understand that this is something is irrelevant. But the computer or the scanner, what it will think, it will take that it is as a data. So that's the next is non-uniform scanning between the front and background data. That is non-uniform. That is just a second. So non-uniform scanning between the front and background data, it is also available. Do you understand? So for example, one data is there, and one that is a front and back data. If you are scanning, means there may be that is again the resemblance of the background data again to the front picture. For example, you might have written in you might have used the one side of paper. In the another side, there may be something is written. But on the other side, you might have taken a computer for that is a printout and a printout of a map. And if you scan that, what will happen? The scanner will think that the background data is also it's a part of this picture, and what it will also take it into account. So the file format, this is the next problem. Next is the file format. There's a non-compatible with the GIS. That is the next one. For example, you might have scanned with some other format. We are having a different format: APK, JPG, PNG, PMG. Like that, we are having the different types of format which is available. But it is not sure that all the formats are that's compatible with the GIS. The GIS is compatible with a particular mode only. But naturally, with the scanning data, will have some other format. It will be get affected. So the time required for producing the compatible data analysis also, it is very difficult. So the scanning, it is a very easier method, but it is having this many number of problems. The electronic data transfer, now what you're going to do, you do the data input methods can create difficulties with the takes more time to address. It is ideal to use the data that is already in digital form. Then it's a question of format type. Then it is going to be. So for example, if you want to take do any digital analysis, at least you should have a minimum data. You should have the satellite data, or satellite imagery, or the data which is acquired through the photograph, or by means of that's a drone photograph. Anything that it should be available. Such if it is in the digital form, it is very easy for you. When you take it in the analog form and then you convert it into a digital form, certainly there will be a lot of questions. There will be some misleading. and there may be some confusion in the digital format. If a format is already compatible with the GIS, then it is very simply a matter of transferring the data, but will likely that doesn't be the case. Will not be likely the case where the transfer, the data transfer often followed by converting data into the usable GIS format is a very easy one. So converting from analog to digital, it is not difficult, but it takes a lot of time. But if you are having already a digital data and if you want to do the analysis, very easy. That's what I want to emphasize in this slide. And next is the data editing. The problems can arise during the data encoding, where the data is error-free upon the transfer into GIS. That is a very important thing. That is even though if you are having that's a digital data, so the digital data at least 70 to 80% only it will be always right. So, for example, I have given an example that you might have taken that is a photograph during the month of April, and you comparing with the photograph with the month of November, both will be 100% different. In the month of November, the area will be marshy, a lot of plants will be grown, there will be more water, and the area will be entirely different. And in the month of April, everything will be dry. So when you need to compare it, that you should understand that these are both the area. But for that, you need to give the geo-referencing. So if you are providing a proper geo-referencing and if you are giving the proper data encoding process, your process will be very easier. So for that, every area, when you do the data editing or data analysis, you should be very aware that there is a proper geo-referencing is given to the particular that is a map. After that, you are going to better to detect the correct errors during this process than integrating into GIS and addressing the errors. Do you understand? Before going to the GIS part, you do the data analysis and you check out the errors. What are the missing data? What are the data which is to be manipulated, or any other data to be corrected? Everything, all the things that should be done with the data editing itself in the prior process or first process. Then after that, if you go for the GIS, then it will be very easy for you. If you are not doing that, and if you are going to directly going to the GIS and do there's a data analysis, finally you'll find that there will be a lot of confusion and your expectation will not be achieved. So detecting and correcting errors, how? For example, the attribute errors are very simple to identify. Very easily you can identify. The methods available for checking the errors. So I have a tool that is been converted to a digital data. Now I'm doing the digital data editing. In the digital data editing process, I found that the data is not up to the mark or it is corrected. So now how to check it? For example, first thing is impossible variable. The values are whether when the range of data is known. For example, negative rainfall measurement. Now the data is giving that at least the rainfall will be 0. Maximum it can be 0 to 100 millimeter or 200 millimeter or 1000 or 1500 millimeter. How can a data can be in the negative? That's a rainfall measurement. So this data, if it is giving, that certainly it is wrong. So impossible values, it is not possible. If it is, further what you need to do is you have to check to the data and find out what is the thing it is there, what is the thing which is there in the format, and whether it is a possible value or impossible value. For example, that is an impossible value. The height of a human, the one tree is 3000 meter. Like that, what is that? 3000 meter. That it is not possible. Do you understand? So like this, you should understand the impossible value or possible value. That means that something has been denoted like the other. Do you understand? For example, there may be a negative fall. It may be taken as a negative rainfall. Do you understand? So like that, the data is right. Data is right, but the interpretation is wrong. Do you understand? So next is that is an extreme value. For example, cross check against the source data. So extreme value. For example, you are taking a photograph of a hotel. In that, it is given as a 50,000 rooms are available. 50,000 rooms, even in the biggest palace in the world, you cannot be available. So this extreme value data need to be addressed properly. Next, internal consistency. The GIS data, the data tools, the total should match with the source data document. For example, you are taking making a survey of an area. In that, you say that that there is a 100 household. You know that this is the street. There are 10 streets are there. In each street, there is a 10 household. This is the picture of your own city. or your own street. Now I am going to take a photograph, and I am saying that in the city of that is someone who is the participant. Is anyone available? Yeah, I'll call upon some participant. Okay, I see that that's Amin Salam. Amin Salam, are you available? Amin Salam, are you available there? Amin Salam. I will call the participant then and there, and I will interact with you. Don't worry. Okay. Yes. I am audible. That's no problem in the audibility. But I am asking about some question to my participant, whether I am that is going in the correct path, or whether you are understanding or not. Like that, I need to verify it is right. So I am calling upon Mr. Amin Salam. Whether available? Abhinaya, are you available? Abhinaya, are you available there? And Dr. Kannan, I think that most of the participants that is just logged it, and that's gone. Yes, okay. I can some Dr. Mr. Balaganesh is there, so I can interact with him. That is Mr. Balaganesh. Yeah. Yeah, nothing there. So I think that, for example, that the extreme value consistency I'm saying, that is up to cross check again. For example, in your Balaganesh, from which place you are coming?
Banariamman Institute of Technology.
You are from Banariamman Institute of Technology. You know that your house is there in nearby area, is right? In which place is in which is your location?
Actually, right now I'm in nearby Trichy, sir.
Nearby Trichy. So in the Trichy, which street you are? You know that you know the geography of your street, and you know that how many number of households will be there in your cities, right? So yes, I am giving that's a value, extreme value I'm giving. So there is a 1 lakh household in your street, in the street alone. Whether you will accept that, certainly you will not accept. You know that there is only 100 house. You are residing out of the city, and it has been newly developed area. Only your house is there. Example I am saying, but I am saying that there is 1,000 number of household is there. That it is a extreme value data. So this data need to be erased, and you should be ratified then and there. And you can unmute Balaji. Thank you. That is you can mute it, please. So the internal consistency, next the GIS attribute data tool should match with the source data document, and where we should find it. So 1,000 or 10,000, or it should be in the realistic data. Next, the scatter diagram. That is the scatter. It is the greatest problem for our that's a remote sensing GIS specialist, where the type of graphing they identify errors in the 2 or more attribute values like altitude and temperature. Because of that's the altitude and temperature, and due to the scattering, what will happen is there are different types of scattering. The scattering may be due to the wind, due to the storm, due to the rainfall, due to the fog, due to the mist, etc. Do you understand? So the last week there was an accident in Kozhikode, that is in Kerala. It is due to the scatter. So the pilot could not see the runway. So it is due to the scattering of that's the data, where from the elevated level the pilot could not see the that is a runway. Because of that, he landed at the center of the that is a runway, and he could not stop the vehicle at the before the runway is ended. So the scattering means that is a reflection of data. The reflection of that's a diagram that it is also available. Do you understand? So these are the errors. You should understand that because of the scattering, the data may be wrong, and you should rectify it and during the data errors. So now detecting and correcting how to correct it now. Now I have told the problem, and I am saying that how we are going to correct this data errors in the spatial data. The spatial data errors are more difficult to identify and that is corrected. The common spatial data errors include the missing entities. For example, you are drawing a line and some lines are missing. For example, I am drawing a line like this. There is a line I'm going to draw. So this line it is up and down, and I find that that is again the line is continuing like this, but this area is missing. Naturally, this area cannot go like this. This line cannot go like this. Now, eventually, this line should be going like this in this format. So this is this data manipulation that you should be very clear that only by the judgment you should make it, and you have to there's a cover the 2 point, and you should check there's a 2 or 3 times. For example, points, boundaries, etc. You are missing means you have to do that. Next, duplicate entries. That is while digitizing, it may have digitized to two or more times. Then you see that there is a clear. You are having that is a for example, you are that is a making that's a digitizing a map. That map has scanned twice a building. Now, when you are digitizing, you find that there is a that is a building like that is a twin towers like this. It is available. 2 building like a twin towers is available. Actually, you know that there is only 1 building. Now you have to identify it and remove this data. This is a duplication of data. Next, mislocated data. For example, in the digitization, this is the road and this is the road, and in the road, this is the you know that this is the ground. But in the there is a digitization. So what happened is this ground has been shifted and it is shown somewhere here. You know that it is wrong. Immediately you correct it. That's all. So mislocated data, you should understand that you need to have the proper georeferencing at the corners. So if you are having the proper georeferencing on the corner and the georeferencing of the that's a polygon, naturally what will happen is you are going to have a total data entity within the captured that's a line, such a way that the data is not mislocated and it being relocated to the correct place. Next is that is a missing label. For example, the polygons are unidentified. So the missing labels, that is the missing label in the polygon. Sometimes the lines and polygons are unidentified. That is for example, a small line may be missing or a small circle may be missing. So next is the duplication of label. A polygon has more than one identification label also. It may be available. There may be duplication. So same street name will be given for another. For one line you are going to given. So one line. This is, you say that this is the Manonmaniam Sundarnar street. This is, and the second that is a route also. You give the Manonmaniam Sundarnar street. So there is only one Manonmaniam Sundarnar street. So this is called as that is a duplication of the label. So you need to understand that this data need to be removed, and you have to give a new name for new value for this data. So these are the spatial data correction. Do you understand? So I have. So these are the detecting and the correcting the errors in the spatial data. So for that, what you're going to do the geocoding and the georeferencing that already I have told. So the converting to address into the coordinate for a map, the geocoding is very, very important. So addresses as an important part of various data store. So most GIS software products are able to do the geocode address, and geocoding is impacted by the data quality, and inconsistencies can exist in the that's address data, such as using street instead of avenue. It is also having some problem, but also the geocoding, because now the georeferencing for even the NAC or NBA, now if they are asking for the georeferencing. For example, you are making a photograph of a particular NSS scheme, and you say that yes, this is the place where we have conducted the NSS program. In that, you should give the georeferencing. The NAC and NBA started to ask the georeferencing, the latitude and longitude, and you should give it. Do you understand? Because while clicking that, they can go to that map in that area and easily found out whether you have taken that's a photograph in that area or not. These are the things that is the technology has been advanced. Understand? So that is so this is the with the I think that I have covered what is the data and what is the problem in the data and what are the editing and the errors and other things that I have covered. So that is now you know the data, and now I'm going to discuss about how to give the input to a data. What are the various sources of input, and which will be given for the data input such a way that you are going to interpret the data, and then you are going to finalize in the digitization format. So I'll play a video. You can understand, and after seeing this video, you can. Yes, can you see the video? Hello? Kannan sir?
Yes.
Kannan sir, can you see the video?
Yes, sir.
Kannan
Yes,
sir?
sir, it's visible, sir.
It is visible. It is playing, sir.
No, sir, it's not playing, sir. It is just on the screen,
See
sir.
that it's playing now?
Yes, sir, it is playing, sir. Playing, sir.
Yes, okay. Whether sound is available?
Sound won't be available, sir.
Three key types: points, lines, which in turn can be joined up to
Hello?
polygons.
Yes, sir, it is sound is very low, sir. Video sound.
Sound is low.
Yes, sir. Yes, sir.
Now, because it's made of
I have kept the maximum sound.
with lines, essentially coordinates, no matter how much we zoom in on our vector data,
Yes, sir. Now it's audible, sir.
nice and sharp
Okay,
and
okay.
crisp on our screen. That's quite different to raster data. Turn on a raster data like here. When we're zoomed out, it looks nice and sharp. Essentially, raster data is like a digital photograph made up of a series of pixels. Zoom in on the screen, see that the quality of the data starts to break down. Individual pixels making up our image. So while vector data looks clear, no matter what our zoom level, raster data is designed to work at more specific zoom levels than do if we zoom in. It's not just the appearance that's different between raster and vector data types. So if we go back to our vector data again, one of the most useful features of vector data is that it not only displays our data on the screen, but we can also add attributes to this data. So we have an attribute table with a number of columns that link to our data sets. And each row within this attribute table relates to a feature on our screen. So as we select different rows, we can see that different features become selected within our GIS layer. And all of our types of vector data have attributes associated with them. So if we open the point layer here, we can see it just has a single column within the attribute table, providing an identifier. If we open up the rows layer, we can see that there's multiple attribute columns giving us identifiers, and attributes tables can contain all types of information, both text and numeric values. And this allows us to carry out various different types of analysis, selecting subsets of the data.
Do you feel any echo?
No, sir.
No,
sir.
It is audible, is right?
Yes, sir. Yes, sir.
Using those attributes. Now, raster data is a little bit more complicated. I've sometimes heard raster data sets referred to as dumb data. We can't do much with it. We can't change things. And I'd argue that that's only true to a point. Now, there's various different types of raster data set that we might come across. So the first example I've got here is a Raster Base Map. And this is reasonably dumb data. There's not too much that we can change about this base map without going into some kind of image editing software like Photoshop and changing the colors, turning it black and white, for example. There are some changes that we can make within GIS, if I figure out which tile I've got on the screen at the moment. In our GIS properties, we can change things like brightness, saturation, we can make it grayscale. So there are various things we can change about this base map within GIS, but there's not too much useful that we can do in terms of manipulating the data. However, base maps aren't the only type of raster data that we have within GIS. So here I've got another raster layer, and this is a digital surface model, so elevation data. And this is one of the things that raster data is useful for, is when we've got data that's continuous across an entire area. So our vector data sets are quite good at displaying discrete objects like buildings, for example. It would be very difficult with vector data to display something continuous like elevation. There are ways that we can do it. We can use contour lines, for example, but there's still gaps there within the data. So by using a raster data set, we now have continuous elevation data across our area. And if we use the info tool here and click on any point, we can actually get the value of elevation, so 87.497 meters above sea level in this instance, at any point across our area. And we can do further analysis with this. So with the raster tools we have available to us, we could reclassify this to identify areas above and below a certain threshold, for example. Or we can visualize the data in different ways. So, for example, rather than grey, we could apply a color ramp to help visualize the data. So it's not quite true that raster data is dumb data, and we do have attributes associated with it, because this elevation value here is in itself an attribute value. And obviously elevation isn't the only type of continuous data that we have. It could be anything. It could be noise levels, it could be pollution levels, it could be deprivation levels. There's all kinds of data that we can represent using raster layers. We want to show it as a continuous surface across an area. And actually what we can do with raster data doesn't end there, because our first base map was a color image. Our elevation data was what is known as a single band image, so a raster layer containing just one set of values. But we can also have what are known as multiband images. So these are raster layers where each of our pixels actually has a number of values associated with it. And actually, any color image is a multiband raster. So color image, by default, contains values for red, green, and blue. They're the three colors of light that we can see, and they're the three colors of light that our computer monitor uses to display the colors of the raster. And if I click on a pixel in this satellite image, we can see that in fact the image that I'm looking at now contains 4 bands. In this case, band 1 will be blue light, band 2 will be green light, and 3 will be red light, and band 4 will be near infrared. So what I'm displaying on the screen at the moment is actually what's called a true color composite image, made up from the blue, green, and red bands. It gives us a true color image equivalent to what we would see if we were looking down from space. But we can actually manipulate this a bit further. We can switch around the bands that we're looking at. So I could change it, for example, so that our red band is actually not displaying red, it's displaying near infrared. I'm going to use green band to display red, and somewhat counterintuitively, the blue band to display green. Apply that, and we now have what's called a false color composite image. So I'm actually displaying different bands, and in this case, near infrared is showing up as bright red, which is showing us where we've got nice, healthy vegetation. Again, we can check that by clicking on that pixel and seeing the value for band 4, which is near infrared. You can see how that's much brighter than the other bands. So while raster data doesn't have attributes in quite the same way that our vector data sets do, it's not quite true to say that it's dumb data. Each pixel does have values associated with it, and we can use those values to carry out further analysis, whether that's a single value like elevation, or whether it actually has multiple values, as in the case of multiband satellite imagery, which allows us to carry out tasks like image classification, which use the patterns in brightness across different bands to identify different land cover types across our image. Okay, and that's, in a nutshell, the difference between raster and vector data types within GIS.
So welcome again. So that is, we have given a clear idea what is the data input and what are the data need to be analyzed, and how need to be the sub-record, all the things that is given in the video. I think that you would have followed that. First, what to input, where that is first thing is that you should understand what to given as an input. So when you know what to give as an input, then only you can understand what will be the required output. So define the, whether I am audible, sir?
Yes, sir, audible, sir.
Yeah, okay. Okay, so first is define the purpose beforehand, and make sure that the data are using for the suitable for your goals for your project, and pre-plan carefully. For example, if you want to do a data analysis for a traffic analysis, you do the different type of data. If you want to do that's a vegetation analysis, you do a different type of data. If you want to plan for that is a highway, or if you want to plan for that's a railway, you use the different types of data. And what are the data associated with the particular that is a thing you need to be collected. Unwanted data is not necessary to be collected. Do you understand? For example, if you want to lay a highway, that you need to be very cautious that you are going to collect the required data for the highway development or highway alignment. For example, the soil data, vegetation data, and that is agricultural data, and maximum flood level, minimum flood level, what is the climate, and all these are the data need to be collected and to be posted there. So when you do a query, and you can easily get the different alternatives for the same origin and destination. So use the most accurate data, but not data that is too accurate for your purpose. Do you understand? So that is the next thing. And check to see if the data are already available. If the data is already available, you digitize it and you do it. Do you understand? So unnecessarily, again, you don't need to start with the some from the scrap. You don't need to start. So the key coverage is that is simple, and use the same map to the extract for the different coverages when it is possible. So one map you have used for highway development, the same map can be used for the railway development also. The same map can be used for the vegetation analysis also, so that one map can be given for the used for the another material. So how much input, that is the scale dependent. For example, if you want to that is make a small area of only 1 square kilometer by 1 square kilometer, you don't need to procure a data for a 60 by 60 square kilometer area. It is not required. Do you understand? The cost is higher, and also it is very complex to locate your data, and for the larger scale. Do you understand? So sample for the more information, that is a more and more information need to be pumped there. So next is you need to you know what is the data, and how we are, what are the data input methods we have seen, what are the problems in the input methods we have seen. Now we are going to do the data into two classifications. One is that's a vector data and that's a raster data. So the methods of that's a vector or that's a raster data that's an input. How we are going to get the manual digitization or registration marker or location of nodes or line not become that's a nodes and building of topology, correcting the digitization errors and transformation and projection, adding attribute data and checking the accuracy of data, the attribute data. So these are the steps in the vector data input. First, the manual digitizing. First, you do the manual digitization of the particular area, and you do the vector analysis. You do the line, and you mark the boundary first. Then you locate the nodes. What are the nodes where it is having the change? For example, the line does not come and the nodes does not become just as a point. Do you understand? So, for example, that is you are having a Nageshwara Rao is presenting my screen. Manala Nageshwara.
No,
Yeah. Okay, sir. Okay. So here, what you are going to do is that is you are going to take care. That's a point. So this manual, when a manual digitization, that is here one layer is available. One layer is available. That over that layer you are going to digitize is like this. And again, the starting and meeting point should be again the proper, such a way that the boundary is closed. So the building topology and the correcting some errors. For example, this need to be a straight line. But in the map, it is in the straight line. But in the digitization, now it is in the curve. Now you need to rearrange it such a way that it can be easily formed. And adding the attribute data. So these are something that some area may be missing. That need to be corrected, and checking for the accuracy of the attribute data also need to be presented. So the methods of raster data input, that is here we have the different methods. Well, that is in that we are going to follow any one which is more suitable to you according to the requirement. First is the presence or absence method. If an object occurs in a cell anywhere, it's recorded as a present. Simplicity is the simplicity that the method is a method for coding, that is it is available or not. For example, that is you make an array. You make an array. That is you divide this area. You divide the area and you find that whether it is available. This line is whether it is available or not. That's all. It is available in which polygon that you are going to give it. So you are going to give it as a presence or absent. That's the first method. Next is centroid of cell method. One, for example, that is if this is a center of the tree. So nearest to the tree there will be some branches. That's all. So this is the thing that you should understand. One household will be there. Nearest to the household, there will be the person, the activities which is associated to the household. For example, near the household there will be a shop. Near the shop there will be a mall. This is a thing which is required for the household. Near the household there will not be something which is not relevant. Do you understand? So household, which you know some centroid point, then you can procure the other data also, which is required for you. Do you understand? So that is very easy for you. And next is the dominant type, which is having the more dominant, which is having the dominant, commonly used for encoding the polygons into the raster format, and it is identified as a present if the occupies more than 50% in the cell. For example, two cells are there. One cell is there. For example, you take two cells. This cell is green color. This cell is green color. Okay. So this cell is green color. Do you understand? This is of green color. Now this cell is also green color. Naturally, this cell should be green color. That's all. Do you understand? So this we call as a dominant type. So the other cells also you should see. Other cells you should see. So for example, this is also green, this is also green, this is also green, this is light green means this area will be absolutely naturally, you can understand that it will be also green. So the missing data can be easily identified and it can be encoded there. So this is called as a dominant method. Next, percentage of occurrence. Not only the encodes presence or absent, but the percentage of occurrence, for example, urban or rural. So, for example, in the rural area, the percentage of occurrence, for example, the greener area means you know that the percentage, the area which is green. One map is there. So, in the map, So in the map is there. So in this map, you see that that is a this area is this is paddy field. This associated area will also be paddy field only. Do you understand? This is a village map. So this you know that this is a picture of a that is a agricultural area. So this is a paddy field means this also may be a paddy field, or it may be some there's a rice that is a some other there's a millet or something like that. It is associated with that. So there is a plan. It cannot be a tower or it cannot be a building or something like that. So the percentage of occurrence also it need to be understood. And generally, these attributes are recorded as a separate coverage. Example: one grid per urban and 1% of rural. That's a percentage of water, percentage of forest, etc. Can be easily that's taken into account. Do you understand? So. This is that's a thing that you should understand. So next is the special that is a raster input. The remote sensing data is to be considered as a special raster data, and image processing software can be used to extract and classify the remote sensing imagery. So the attention should be made to the geometric and radiometric correction to the method of classification, and institutional problems related to remote sensing data include the availability of data, limited coverage, cloud cover, cost, education, etc. Training artisan also be nullified. Otherwise, then you are going to get the proper data. Now, the data input you are given, and you are going to digitize it. How you are going to digitize? First, you load that is a legend into a layout. You are going to load first. You are going to scan the map, and you are going to feed as a background. So I think that everyone are well versed with the AutoCAD. In AutoCAD, you like that you have different layers. So in the arc view, you can create many layers. So in that first layer is the base map, and the second select the legend in the right click and like to simplify, and this will separate the legend, and you can add any number of legend, 1, 2, 3, like that, 100, thousands of legends you can add. Now you can edit each and every legend. For example, that is this is one layer, and this is another one layer, and this is another one layer. Like this, the layer will be there. Each layer, for example, this will be vegetation. This will be that is a urban development. This may be road, or this may be buildings, etc. All this map you are going to give the final map. Combining to that, all the map you are going to give the combining map. So now what you are going to do? You are going to put the legend properly. This is vegetation. This is land cover. This is that's a road. This is road. So this like this you are going to give it, and you are going to that's a develop the map, and in the layout select the file, and which the layout of the which should be to the JPG format. But before, make sure that the JPG image support extension is loaded in your digitization tool. So now your digitization is process over. Now you are going to do it with the you're going to do it with the next process. Now you are representing the georeferencing. Already we have told about the georeferencing. By georeferencing, this now how to describe the geographical features. First is that the spatial data, which describe the location. Hereafter, these keywords will be used then and there in the coming slides. So that is the spatial data, which describes the location, and that's the attribute data, which specifies the characteristics of the location, what, how much, when, and etc. That this is called as attribute data. Spatial data means it is describes the location. Madurai, it is the Meenakshi Amman Kovil is the that is a spatial data. Attribute data, you give the characteristics about the location. It is located in this latitude and this longitude, and it is the what is the length and breadth, and when it was the disability, like that, this data is called as attribute data. So how do we represent this digitally in GIS? By grouping into the layers. Already I have told with the grouping into the different types of layers, and finally you are going to get it. For making the vector data, you can use the arc info or shapefile or arcview. For using the digitizing the raster data model, you can take the grid or image in arc or arcview, and by selecting the appropriate data properties for each layer with respect to the projection, the scale, accuracy, and resolution, we can develop the database. With the database, you can do a lot of wonders. Only the development of data, it is available. For example, I want to make that is a digitization map, and I want to see what is the that's urbanization from the year 1950 to 2010. In the period of every 10 years, you can easily make a query and you can find out how this in the 2010 it was like this, 2015 it was like this, 2020 it was like this. Like this every 5-year period or every 20-year period or every 100-year period, whichever the data which you are having, that it can be easily rectified and it can be represented. So this we call as a database management system. Where the GS data structures we have there's a two we are going to follow with the two data. One is raster data, another one is vector data. So how we are going to give it? So the raster data that's a length in run that's a compression, and there's a quadry representation, and the DBX representation is also available in the any file format you will accept. So the vector data, the whole polygon, point or polygon, node, arc, polygon, things, anything that it can be, that is used for representing this kind of a vector data. So before going into that, there's a deep into the spatial data and the data analysis. You see this video, you can have a more understanding about that. And again, I will start with the spatial data types. Whether it is audible?
Yes, sir. Yes, sir.
Is audible, is right?
Yes, sir. Audible, sir. Sir, video sound is somewhat low, sir.
Yeah, that's what I'm adjusting.
Yes, sir. Yes, sir.
Now it is okay?
No, sir. Sound is not coming, sir.
Okay.
Sir, the audio of the video is
Yes,
not.
sir. Audio not available. Sir, again, I'll improve, sir. Just.
Yes, sir. Audio is not available, sir.
Yeah.
Civilization. Water provides life. Water is greatly in depth and water volume. Sure, it's pretty obvious. Every well has a spatial location.
Yes, sir. Yes, sir. Okay, sir.
Imagine that for every well that was drilled, someone mapped the location and the date the well was drilled. I think it would be pretty cool if we could animate when the wells were drilled. For a given region, this might provide an indication of the growth over time of human civilization. I've opened a fresh copy of ArcMap. With the catalog window open, we will expand the subfolder called Wells. We see a wild geodatabase called Project 404 and a feature dataset called Wells and a feature class called Montana Counties. We will drag the counties to our map while in DataView. Double click on the existing symbol and change it to a hollow symbol and click OK. Once again, open the catalog window and drag the feature class called water wells to our project. Let's view the underlying attribute table for water wells. Right-click, open attribute table. There appears to be a field describing the type, which is a well, the total depth of the well, the yield in gallons per minute, and a field indicating when the well was drilled. This is awesome. We need a date field in order to animate or use the time slider time-enabled, temporally amazing ArcGIS desktop option. So what do you think? I'm overly exuberant about this time-enabled mapping of spatial features? Well, I hope you will be too. Just wait and see. This is pretty cool. We also observed that there's over 222,000 records in this data set. Next, we'll set up the foundation so we can use the time slider window. Double-click on water wells in the table of contents to invoke the layer properties dialog box. Make the time tab active. All right, this is pretty simple. Place a checkbox next to enable time on this layer. As we observed earlier, the geographic information asset storing information on wells has a single time field, as opposed to a start and end time. The field in the attribute table storing the time information is called comp_date. We'll choose it from the pull-down list here. The format of this field is primarily date, though we'll choose date/time. We'll set the time step interval to years. Apparently, some of the well data dates back to the 1800s. To determine the layer time extent, click the Calculate button, which will automatically look at and analyze the range of dates within our time field. From what I observed, the data does change frequently, so we'll place a checkbox next to data changes frequently, so calculate time extent automatically. We don't necessarily need to set the time zone, but this is data for Montana, which is in the Mountain Time Zone. All right, very good. That should at least set a foundation for us to create an initial time slider or animation map. Well, I believe, there's a lot of wells in this geographic information asset. And let's make it happen. All right, next we will click on the time slider icon as part of the tools toolbar. You may note that the time slider window has a level of transparency or opacity, which may seem a little funky, though there's a reason for this. By adjusting the transparency of this window, we'll be able to see the controls and the underlying data. Therefore, the animation we're about to perform won't be obscured by the window. To modify the transparency of this window, click on the options icon from the dialog box, make the other tab active, and then adjust the time slider window transparency. Let's play the animation using the time slider window. Click on the small play button here. As the time slider bar moves, we are presented with map information, spatial data, along with a timestamp indicating the approximate temporal snapshot of the data being presented. And what's interesting about this animation is we are being presented with a series of data flashes. These flashes reflect the spatial locations of the wells and provide an indication of the temporal period of when they were drilled. Sure, this animation has the potential to be useful, though let's make an attempt to retain all of the points representing wells from the beginning of the animation to the end. Let's invoke the time slider options. Click on the options icon, make the time display tab active. We'll set the time step interval to 2 years. For the variable time window, we'll enter a value of 200 years. Therefore, we'll be able to see a total of 200 years worth of data. Other options we could adjust include a time extent and the playback speed, though we'll keep these for the most part the same, and then click OK. Our hope is that the time slider window will let us visually analyze the spatial locations of the wells and the temporal or time period during which data were collected for this spatial asset. This is often referred to as the transaction time. The term transaction time is the time period during which the fact, or in this case, the well information is stored in the database. Well, let's make it happen. Click on the play button. It appears as if during the early 1800s, note the years being shown here, there is very little activity, probably because there weren't a lot of people, and it's settled in Montana at this time. Let's see what happens after 1909, which is when the Homestead Act was revived, and it greatly affected the settlement of people in Montana. This Homestead Act, in a sense, gave away free land of up to 160 acres per family. And then, of course, the horse was replaced with the automobile. More roads were built, more people moved here, more people needed water to irrigate their crops. And holy moly, those are a lot of wells. Viewing temporal databases that store the history of an event can tell a pretty powerful story. Although the scale of this map is relatively small and the points are really tightly clustered together, we can observe a series of patterns in regions that have many wells. Let's try this. Let's zoom into the northern part of Gallatin County and rerun the animation. Presenting a larger scale map will reveal more detail in this area. Once again, we can see clusters. Now, note that currently in the table of contents, all of the wells are being displayed with a single red dot. We're not limited to this. We can modify the symbol in any way we wish. The time slider window will use any symbol we establish for our spatial data. Let's try this. After invoking the Layer Properties dialog box for the wells, click on the Symbology tab. Let's use a graduated color symbol showing the yield of each well in gallons per minute. Let's use graduated colors, and the value field will be set to yield. Click Apply and OK. Now we're being presented with even more information. The wells represented with a darker color apparently had a greater yield. When working with spatial data, if we don't know that something exists, it doesn't mean that it doesn't exist. Dr. Carl Sagan, the astronomer, once said, "The absence of evidence is not evidence of absence." We need to question every spatial data set we use or receive. Just because there's an absence of evidence, or there aren't wells in certain locations, does not necessarily indicate that there's evidence of absence, or in other words, that wells do not exist there. Maybe they were not mapped, or maybe something happened to the data. Data may have been lost. We have been hired to work with a documentary film producer who's creating a film on the American West and the settlement of the Western territories after 1830. They would like to incorporate the well animation into their movie. Let's export the animation to a Microsoft AVI file so that the producer of the movie can use it. For reference, we've added a high-resolution proprietary satellite image of Montana. Focusing on the time slider window, let's click on the small graphic icon that looks like a strip of film. In the text entry box next to file name, we'll enter a new name for the animation. To view the video export properties, click Options. To modify or enter a custom frame per second rate, place a checkbox here and then enter the new frame rate or the total number of frames. Let's modify the horizontal and vertical resolution. Place a checkbox here. We'll enter a horizontal resolution of 945 and a vertical resolution or a height of 576. After clicking the export button, we're presented with a video compression dialog box. We'll keep the compression quality set to 90. Note the compressor is set to Microsoft Video 1. Click OK to begin the export. Before exporting the video, we may wish to click on the Options button. Open the Time Slider Options dialog box and click the Playback tab, and then select Play and specify duration. When creating a high-resolution video, sometimes exporting the video without a codec or without an encoder-decoder method, the output video will be much finer in resolution. Another option is to use a video codec that does not use lossy compression. A wide variety of free codecs are available for download at www.free-codec.com. The number of frames per second in the export video can make or break the video. If the value is set too low, we may lose some of the important animation as part of our video.
I hope you understand what is the data, how it has been procured, and with the data analysis, what they are doing. For example, the case study has been given. The case study has been given for that is a borewell tube. So how for the 200-year data, you can see that how it is the data has been interpreted and it has been done. Okay, so like this, that is the spatial data types. where it is having that's a continuous elevation. For example, continuous elevation, rainfall, ocean, salinity, etc. Where the unbounded area, where there's a bounded city, are moving the air masses, the network nodes, fixed are this you call as it can be covered with the spatial data. So the attributes type of data are these are data types, where the database management system it is occur in the parcels, like in the key field, and you give that's a, for example, address and the name, the main sheet with all the thing that it has been added to the particular that is a GIS that's a feature, where you can recover the relational that's a data in any format, and you can do the data analysis. Now, the data, the raster and vector data, in the nutshell, you can understand very easily. That is, if you understood what is the data and what is the raster and vector data, then only you can understand the further proceedings. Okay, so the raster data, anything which is represented in the pixel, that is called as a raster data, and vector data, it is anything in the line, polygon, other thing that is called as a vector data. So, for example, that is you are having a this is representing in a small cells. So this is called as a raster data. And if you are representing in a line, for example, in the line, for example, if you are making a boundary, this boundary, and you say that this is the area we called as a raster data. And if you are representing like a line, the road map, or a thing that we call as a vector data. So integration of data, raster data and vector data, you will get the real world data. The integration of raster data and vector data, then only you will get the real world data, such a way that because studying with only the raster data and vector data, and you cannot do the complete spatial analysis. The spatial analysis will depend only upon the raster and vector data. So you should, before going into that, deep into that, you should understand what is a raster data and vector data. Raster data, it is in the pixel form. Vector data, it is in the that is a line or a polygon or the dot or like that. It is in the form that you call as a raster and vector data. So the raster data model is a location represented by the grid cell, where it is a location by the x and y boundaries, and the attributes are represented in a single value for the single cell. Attributes are represented by the unique ID number to the table, and the table which is shown here like this. That is you are going to give for each and every point that you have a label. So this we call as that's a vector data, and much data comes in from the images of the remote sensing. Here, much data comes from the Tiger files or DLC, USG forms, and the best continuous features are elevation, temperature, soil type, etc. It will be represented by the raster data, and the best features with the discrete boundaries, that is property lines, political boundaries, transportation, etc., will be useful for representing with the vector data. So here, the concept of the raster and vector data, it is like this. Here, for example, the raster representation. So here you can find that is a red color. For example, here I'm going to draw connect these dots. So for example, the R and all, I'm going to connect it such a way that this is the this is the red color. So next is that I'm going to make another one that is a representation with this, that it indicates this road. This indicates the road, and the T that represents the that's a tower, etc., and house is there. And here, with the help of this, that you are going to make up, that's a vector representation with the line and the polygon. You are going to make it. So overlapping of raster and vector data. Finally, that's the image will be obtained. This image will be obtained. So raster data, it is in the cell form, and vector data is represented in the line, polygon, or point form. That these are the concept of raster and vector data, where that is you need to do the data analysis accordingly. Do you understand? So the vector data, the points are represented with the discrete point features, and you are going to take a data. For example, this point, and this point will be, for example, it is a airport point, and this point that's each point will be that is here. For example, here you are going to give it with the that is. Here you have here you are going to represent the airport. So this airport here you are going to give all the details for this particular airport. So this is the next is that the lines represent the linear features. For example, this is a right line. So this is the boundary line. It gives the desert line. So this may be a polyline. What is the node and what is the T node and what is the your latitude, longitude, everything. It has been given there. And then the vector model, for example, you know that it depends upon the x and y coordinate. So x like this, that it will be distributed, and you are going to draw the vector data. And the vector data model, it is very easy to understand, where the polygons represented by the bounded area, and this is the picture showing the vector data model. So the vector data model, the points are discrete, and the nodes, vertices, and the lines, nodes, vertices, and arcs are used. So the vector data model, the formats are available in ArcGIS and ESRI and the CAD files and other thing that it is possible. And the vector data model, that is the ESRI geo database also can be used. So in the vector data model, ESRI shape files can also be used for making the vector data model. So the vector data model shape files polygon are given as an example here. So district or a state map, it can be that is done with a very that is a easier way that easily you can identify it. So the vector data model, ArcInfo coverages, where the commonly founded format the data model are more complex and display more slowly in the ArcGIS, and the coordinate are not editable in the ArcGIS, and the problematic there's a OS file structure. So next is the vector data model. Here, this is ArcInfo coverage spatial data model. The polygon shapes are boundaries and lines. Some topographical rules can be built up in the database. So the same boundary, the boundary of different colors of that it can be that is made with the this boundary such a way that the colors can be distinguished. So these are the vector data model. So that is easy to obtain with a variety of sources as GPS, traffic survey, directory, etc. So next is the vector data model characteristic. So next we go on to the raster data. So the raster data, you know that it is with the cells. How whether the intensity of cells here and the cell size are equal, and the cell length is also equal. So now with the raster data model, you are going to do the few different types of raster data model. It is shown in the picture. So the same, there's a digital photo. The digital photo has been digitized in the raster data, and the final output is given here. So this is that's an example for a raster data. So raster data characteristic, the rectangular grid of square cells are given there, and that is some of the satellite data images that can be NOA or US, MODIS, Landsat, Spot, and Iconus data or QuickBird. This can be used for the data analysis. So the ArcGIS data set also, that is it is extended for shapefile, shape index, or database table, and ArcGIS can be used. So these are the Arc catalogs. And this Arc map can be used for displaying, editing, queuing, analyzing, charting, and reporting. And Arc tools can be used for making with the GIS. That's a map here. So these are the maps and the database for an interactive. So as given in the that's a video, you can once you procure the data, you can do the different types of analysis. So you're representing the pixels. So this is the way the data is extracted, and the layers of the roads, and that is you can see that the roads are yellow and blue color are the rivers, and can be easily seen from the air satellite photo. And this image being digitized, and you can see that and be in the digitization format. For digitization, so this we call it the digitization. So manual digitization, automatic scanners are there, direct entry. So and that is we are going to do it with that. So next is the input of spatial data. Continues here. The modes of input are grid overlay, and a keyboard or digitizer or scanner can be used for making this digital input. And the input that's already it has been described. So the data output. Finally, the data output will be the presenting the maps and the data. The audience or the information cutter, knowing who is your audience and knowing what is the information to present them. So the showing data to a general public should be simple and easy to read, and knowing the data, how many maps you need, how much details you need, how much the themes you need, how many features you need. So these are the data output. Only on knowing this data output, you need to integrate the data and you need to present it. Do you understand? So there's a GIS function. It can be with a table, or it may be a map, or interactive display, or 3D. That's a display will be the data output. And these are the file formats which can be used for as given in the appendix. So normally these are the softwares which is used for. I'll share this PPT. You can use it for your future purpose. So according to this, the research issues in the spatial data processing is that is anyway. As a researcher, I want to throw some light on the research issues. So that is here the spatial data process missing data. For example, if data is that is by using the fuzzy data or data volume data, space volume data, you can that is do the data processing. And the spatial data sharing management, metadata, GIS data, attribute data, and distributed centers update such online analysis also can be done. And the integration of CGS, GIS with the natural and social information can also be done. And the development of new methodology and tools for spatial data analysis, sampling, survey, clustering, etc. can be done. The application of GIS database and new technology in the historical and the other studies can also be made with this GIS platform. So I have touched only the tip of the iceberg, because this area I have given with the fourth topic. The fourth topic is extreme. That is, it is a one unit, that's a chapter in a subject. Within 1.5 hours, I was asked to cover the whole. That's a topic of 4 different areas. So I could not meet up with the presentation, but just I have touched in all the area. But in the detail, the presentation I have given all the data, all the information. I'll share it, and if you have any doubt in the future also, you can contact me and you can clarify your doubt. So thank you. So thank you for the opportunity given by Dr. V. Kannan. That is for giving me this opportunity to present before this August gathering. So thank you very much, sir. If you have any doubt, we will discuss. Otherwise, we'll close the meeting.
Dear participants, if you have any queries, kindly post in the chat box. Sir will reply.
So I have told him that that's 90 minutes. I will cover the presentation. I have covered it exactly at 90 minutes, and I'm giving some 10 or 15 minutes for discussion.
Sir, the participants are posting the questions in chat box, sir.
Yes, sir. Please, sir. You can. That is, sir. So I think that there is no questions from the audience. So we can conclude, sir. Thank you. Dr. Kannan, you can conclude.
Yes, sir. Thank you for sharing your valuable thoughts with us, sir. And thank you for your precious time, sir.
Thank you, sir. Thank you.
Thank you so much, sir.
I'm giving my email also in the chat box. Okay, if any query in the future, you can post it to me. I'm sharing my that is a so some questions they are asking. So what is the difference between the geometric and the radiometric correction? So the geometric correction here, you are going to do it in the georeferencing with the digitization format, and the radiometric correction will be doing with the the next extreme level, where that is with the known one point, and we are going to identify the other point that we got as a radiometric that is a correction. So someone has asked, what is geocoding? So geocoding, it is a representing that is a particular point in a so Sumit Sen has asked a question. that is what is a geocoding. So, for example, that is a geocoding means with a representing to a particular point, and you are going to give the data regarding to the particular point that you got as a geocoding. So, for example, latitude and longitude, it is an example for a geocoding. Yes, sir. Any other questions? When we use geographic coordinate system and when we use geographic coordinate system and project the coordinate system, yes, we can do it. What is Jyoti Bora asked, what is scattergrams? Yeah. Yes, sir. Jyoti Bora has asked, what is scatter diagram? The scatter means, so for example, if you throw that's a glass over a table, what will happen in the platform or in a ground, what will happen? It will scatter like on all the area. Like that, what will happen is when the light passes through the sun view, that is, for example, water or any other material, what will happen? It will be distributed to that near area, and what will happen? The picture will not be very clear. So your light will not pass through that, and it need to be reflected. The thing is, that is the concept of photography is you send a light, and again this light will be coming to you. That is only you are going to record. If there is no reflection, you cannot see anything. Now we are able to see everything is only because of the reflection of that's a light. So like that, if the scattergrams is available, what will happen is the light will go there, but it will not reach you again. So if it is not reaching you, certainly what will happen? You will not get the correct picture. One such example is that is there is lot of the mist inside the room. In the mist, if you take a photograph, what will happen? You will not see the face clearly. Why? Because the light is not reflected again to your camera. So this we call as scattergrams. Okay. Thank you, sir. Thank you, Jyoti Bora. Any other questions? So I am giving my cell number. Also, you can WhatsApp me or you can call me. Okay, you can WhatsApp me or call me, and you can clear that out. In future, we can also do in the interactive research in the area of remote sensing images or in the transportation or in the concrete technology. So I am a versatile person, not confining to a single that is a subject. So I request the participant in future, if you have any doubt or if you want to interact with me regarding the facilities, and if you want to use any facility like a XRD or we have wonderful IRC, International Research Center, with all the facilities. So if you want any that is a facility to be used in Kalasalingam University, we are very happy to extend our help with at least with that is a free of cost in the first level, and in additional level we will give some discount also for doing any research activity or conducting of any test or XRD or this Laplace that is a transformation test or that is a digital scanning test or anything which is required for the research. That it can be done, and we are having a wonderful network laboratory funded by the TIFA Core, and you can use this facility. Thank you, sir. Thank you.
Thank you so much, sir.
Yeah.
We can conclude, sir. Thank you, sir.
Yeah, I have concluded, sir. You need to post the vote of them. That's all.
Okay, sir. Okay, sir. Thank you, sir. Thank you for sharing your valuable thoughts, sir.
Yeah.
And we are looking forward for your constant support, sir. For our.
I'll be there with you. Thank
yes,
you.
Sir. Thank you, sir.
Shall I leave, sir?
Yes, sir. Yes, sir. We can leave, sir.
Yeah. Thank you.
Okay, sir. Thank you, sir. Dear participants, feedback link has been shared in the chat box. Kindly complete the feedback.